So today I'm going to talk about SPHEREx, which is an all-sky infrared spectral survey satellite. And this telescope just launched last month in March, and it's designed to do all three big questions here. And the name itself kind of says it too, as you heard. So SPHEREx stands for Spectrophotometer for the History of the Universe, Epoch of Reionization, and ISIS Explorer. This is a very neat telescope, and today I will introduce you to the design of the telescope and what science goals we are aiming for, and especially also highlighting the involvement and collaboration of CASI, 한국천문연구원, um, for this SPHEREx collaboration. And then I will finish with some nice videos of the launch event. All right. So this is a cutaway view of the SPHEREx telescope. Um, and as you can see, oh, let me tell you a little bit further here. So you see the Earth here. So it's a satellite at the lower Earth orbit, um, and it's observing in infrared. So the thermal shield is important for this infrared telescope. Um, for this telescope, we don't have any active coolant, and the cooling happens passively with these photon shields. And this can cool the telescope down to 80 Kelvin. And where the focal plane unit is sitting, it's going to be down to 55 Kelvin. And when it observes uh, the universe, the light comes into the camera, and then it's split into two detector arrays, where uh, there's a dichroic beam splitter that sends the light into two arrays of detectors. And this slide, I will show you how the telescope is generating the spectra of, spectrophotometer. So you may have heard the spectrophotometer before, or if it's the first time, this animation introduce you to the concept very nicely. Um, so on the top left, these three squares represent the detector arrays in the shorter wavelength, and the on the bottom three squares, these represent the detectors in the longer wavelength. Um, and we and the what's oh, and as you can see, we don't have any spectro, any grading that generates a spectrogram. What's going on is actually we have infrared detector, and then on top of the detectors, we have a filter called linear variable filter. Um, and what it does is it transmits defined wavelength bands uh, where the central sensitivity varies linearly across the filter. So the photons that passes through the filter at this position will be at at a shorter wavelength, and and the one it passes through the filter at this location will have a longer wavelength. So when you point the telescope to an astronomical object, like a galaxy here, and you take a picture in one position, then along that part of the detector, those will image uh, the source at that wavelength. And each exposure, we are taking about 2 minutes of exposure, and then we slew to a different position. So the source falls onto different part of the focal plane. Um, so In that way, we can complete a spectrum of this object uh, with these cadence of the pointing. And we have defined 51 spectral channels across all these six um, detectors. So after 51 pointings, you obtain a full spectrum of the galaxy. And this movie will show how SPHEREx is observing. And the SPHEREx is at lower Earth orbit along the terminator line, which means it's always 90 degrees away from the sun. And there are certain criteria to avoid, such as the air glow from the Earth, Earthshine, and moonshine, etc. So this shape defines the allowed position where it can point to. So it takes 2 minutes of exposure and slew a little bit, and then there's a large slew to stay inside this allowed area of the pointing. And here you can see a few spectral points are obtained, but to fill up the full spectrum across the whole sky, it takes about 6 months to do that. This is a very high speed um, movie of what's happening. So the SPHEREx orbits along this terminator line, and then it accumulates all the spectra. And about 6 months, it fills up everything. And you may have noticed that because it's following the orbit in this shape, we're visiting the ecliptic pole at the North Pole and South Pole more often. So we can have many more exposures around the northern and southern caps. So we can have deeper
Yeah.
sensitivity around that region. I'm sorry? Oh. And in the end, this heat map shows a number of hits um, from all those 102 spectral channels. And you can see that in this coordinate system, these two blobs are the north and south ecliptic pole area. So that's the where deep fields are located. Okay, that's how SPHEREx is observing in orbit. And now I will tell you the three major science questions that SPHEREx is addressing. So the first one is asking, how did the universe begin? And then the second one, how did galaxies uh, begin? And the third one, what are the conditions for life outside the solar system? Um, these are very big, distinct questions, but the data from SPHEREx can answer all these three questions, and that's the three major science goals. And along the way, we will produce a unique all-sky spectral survey. So with that data set probably published to the public, um, the general astrophysics community can use the data set to find other novel things. So I'll go through each of them. The first question, how did the universe begin? This is a cartoon plot of how the history of the universe. On the left, we start from the Big Bang, and then we have some afterglow of the Big Bang in the form of cosmic microwave background. And then later, stars are formed and galaxies are formed, and then it appears as it is at the present time. And what SPHEREx will do is to observe um, the galaxies and um, measure with the spectral survey of those galaxies. We obtain catalog of redshifts to those galaxies, which will give us information of how the three-dimensional distribution of galaxies are. Um, and that's important to understand actually what happened at the very beginning of the universe. The theory called inflation that explains how the Big Bang started in a fraction of a second here, 10 to the negative 32 seconds. Because here's another cartoon plot. So the theory of Big Bang is well established um, from CMB and onwards, but uh, there were some problems with the Big Bang theory, and about 45 years ago, uh, there came a theory of inflation which explained how the Big Bang started, what type of physics exploded the expansion of the universe at the start of the Big Bang to resolve those problems that the then Big Bang model had at the time. Um, but to understand what actually happened there, there were different types of exotic physics that explains the inflation behavior, which can lead to different consequences much later time. So, um, at the beginning of the universe, where there is underdensity and overdensity distributed across the universe, those distribution grows into structure in the distribution of galaxies in a later time. And depending on how um, that exotic physics happened, uh, as explained by this first top half and the bottom half, the consequences may be different. So what SPHEREx will measure will um, let us know how this large-scale cosmic web is distributed to distinguish the picture from the top and the bottom, which can tell us whether that inflation physics happened from one theory or the other. And going on to the second topic, um, we are going to study how did galaxies formed and evolved over time. Um, so this is also a similar cartoon picture, but kind of focus on the formation and evolution of galaxies. Um, from the hot Big Bang, which was predominantly from helium and I mean hydrogen and helium, and then later matter formed stars and galaxies, and then the stars light up and then ionize the neutral hydrogen around that. And this cheese-shaped thing is uh, describing that phenomena, and we call reionization. That's the epoch of reionization part in the name of SPHEREx. Um, and what SPHEREx is doing in this picture to understand the galaxy evolution and formation is to collect the light, um, background light as a whole. So instead of detecting like single point galaxy as sources, SPHEREx will make map of diffuse light that's coming from all light sources, also including some stars stripped out of galaxies during the evolution of galaxies, and the really unresolved, very far away uh, old galaxies that formed to reionize the universe. Um, Here, this picture will illustrate that concept a little further. And I need to emphasize that this type of mapping is happening in the deeper survey instead of the full sky survey, because we want to collect all the faint diffuse lights in each color. So Here we see some distribution of light, but if we have only detection of bright point-like sources, you will get this information only. But this is hiding all the rich information that's coming from the diffuse light across the history of the universe. So what SPHEREx does is, even though it's a small telescope and lower resolution, instead of um, detecting each individual galaxies, it collects all the light from all sources. So it can see this diffuse map of the background light. And it has 102 channels, so it can prove the diffuse map at different colors, um, and that'll help tracing uh, the different background light sources from different redshifts and different time of the universe. And it'll help us study the components that contributes to this diffuse light, whether it's coming from dwarf galaxies at the very early universe or diffuse emission from stars strip away from galaxies, things like that. And lastly, the third topic is regarding the origin of biogenic ices. Um, this is important to understand how the water or other biogenic ices came from in the universe. We have a lot of water in on Earth, but where did they come from? So SPHEREx will look for some fingerprint signals uh, from star forming regions and protoplanetary disks in young solar systems where such ices can be present. And it shows its fingerprint in the signal in this spectral survey as absorption features like these in the top left plot here. Um, and this is going to be really a game changer for finding sources and studying the distribution of such sources. And this is showing more than 8 million targets could be available on the in the Milky Way. So this is galaxy latitude and longitude, and these are the targets. And with all these information that will be available after the survey of SPHEREx, we'll have a lot of data available to the community. And like the other legacy data that astrophysics community benefited from, such as Kobe, IRAS, or other satellite missions on the full sky, SPHEREx will be a unique opportunity to contribute the astrophysics community by providing complete near-infrared spectrum from 0.75 micron to 5 micron on every pixel of 6 arcsecond size. And briefly introduce the data release cadence, uh, the calibrated spectral image will be available every 2 months since observation time. And following the second and fourth survey, the images will be recalibrated and then updated images will be available. And on the left, you see the science team meeting photo. And the group of people in the science team meets regularly. And later at the end of the mission, we will have a full, sorry, science, core science product as well. And for the data, um, the URSA, the Infrared Science Archive at IPAC on Caltech campus, will host the data as well as it has hosted other telescope data in infrared. So SPHEREx has a landing page there Not much is there right now, but that's where you will see the data available in the future. And I will touch on the collaborative effort between 천문연구원 and NASA on this. Um, so a big contribution from Kasi 천문연구원 is that it developed and delivered the SPHEREx testing chamber, which is resembling the environment of the space um, and lab to test various things for the detectors and camera. And here I will show what happened. So in 2022 summer, the chamber was delivered from the Kasi team, and it was used for various testing. And for example, this video shows the assembly of the camera inside the testing chamber, um, which will be later used in the testing facility, also in the lab at Caltech, to check the focus location of the detector and the also the spectral responses on the detectors. Um, so with that, I will emphasize two important testings out of all the other important testings. Um, so first one, the focus testing happened during the thermal vacuum testing at Caltech with this Kasi chamber. Um, so we have the detectors on the focal plane, and we need to check the alignment of the focus location. And if needed, we need to adjust it. We have to do it before going to the space because you cannot change that in space. And after the second run, the focus test meet the requirement within the tolerance. Um, because it's a space telescope, it has to survive the vibration during the launch. And we do that. So after the vibration testing, you also check whether the focus is still reliable. And it happened all in the Kasi chamber in the lab space at Caltech. And another thing is the spectral response check. So on the right, it shows the bandpass response from the start positions in this detector. So you can see that it has well-defined bandpass as designed here. Okay, and fast forward after all these tests from Caltech and uh, and many other tests. Uh, Last month in March, I mean, it already went there in February at the Vandenberg Space Base. Um, SPHEREx telescope was integrated with the spacecraft provided by SpaceX. Um, and here you see the SPHEREx and then the fairing cover that protects the telescopes while it's launching. And SPHEREx had a co-writer for that launch. They are four other telescopes for solar physics called Punch. They are they are aligned. I mean, they are located here as well. Um, and that's the assembled rocket. That's the fairing we saw, and then the bottom is the Falcon 9 booster. Uh, and I'm going to show you the launch video. So it launched on March 11th after many rounds of delays. Um, and now you see the booster separated and the second stage start burning. Um, And you will see the fairing comes off, exposing SPHEREx here. And at the altitude, 675 kilometers, um, SPHEREx is separated and successfully placed on the orbit. And after SPHEREx is separated, the punch satellites were uh, separated also. Okay, that was the launch event. And after about a little bit more than 2 weeks of in-orbit checkout, um, on March 27th, it produced the first light images from all six detectors here, as you can see. Um, the SPHEREx is still undergoing the in-orbit checkout until the end of this month. And the science survey will start from May. But this first light announcement shows how awesome the telescope is um, operating and kind of anticipating a lot more discovery coming up. And here you see some features like air glow from the Earth atmosphere and some bright stars. And if you zoom in this area, you see some nearby galaxies and also some faint galaxies detected too. And then because there are two arrays of detectors on the same field of view, the top detector is seeing the same sky as the bottom detector. So you can see some stars aligned together, but at different intensity. That's basically showing that we're making a spectral imaging at the same time. Um, yeah, so with that, um, I will just remind you of some timeline that comes out from uh, that is for SPHEREx. So right now we're under the in-orbit checkout, and then the survey will start in May, and then after every 60 days of observation, the data will be available to the community. Okay. And thank you for listening to this talk. And for more information, you can also check out the collaboration webpage here.